position is the generic equation is some amplitude times the cosine of omega t plus some phase shift, depending upon where you start the clock. Now I'm starting the clock at the moment I let go down at the bottom, so it starts at that maximum value as soon as I begin. So that phase shift is 0. My amplitude is given in the problem, so that's 1 meter times the cosine of omega, which I crudely estimated to be 1.5 meters per second. Sorry, not meters per second, that is wrong. That's radians per second, I did write it correctly over there. Times time. So there's my equation for position. I'm asking when am I a half meter above where I started, so that's on the negative side. So when is 1 meter cosine of 1.5 t, just drop units of the 1 there, is equal to negative 0.5. Which is 2 pi over 3. And so t would be roughly 4 pi over 9. Which crudely I'm going to say is 1.3 seconds. Now do we want to use the actual numbers or crude estimates good enough?
That's fine.
All right.
As long as you explain,
All right.
it's fine.
Now it's going to be within that first period, because the question is asking what times, and I underlined and boldfaced the S. It's going to hit that point twice, because it's going to pass it going up and it's going to pass it coming down. There's symmetry abound in this thing. There's 2 ways I can figure out what that time is for the second part. Let me do the more difficult way first. If I think about angles here, flashback to trig, unit circles. If this is -1, then that's 1, 1, -1. The cosine of some angle, so if I have some angle right here, theta, the cosine of theta is just equal to the x value of that spot. So it's going to hit that x value there and there. That's -0.5. After I divide by the amplitude. So if it's -0.5, yeah, it's going to hit it twice there. So this equation right here is basically solving for the time at here, 1.3 seconds, given my crude estimations. My period is sorry, I was about to do it the easy way. I know it's also going to hit it down here. So if this angle right here is, well, assuming it's 2 pi over 3, which means that this angle right here would be pi over 3. That means this angle here would also be pi over 3. So it also want to know when is 1.5t equal to 4 pi over 3. In other words, this angle right there. Because the calculator is only going to give you one answer. When you do the arc cosine of 0.5 or -0.5, it's going to give you either a second or fourth, it'll give you a second quadrant angle. It's going to give you this angle right here. Basically, that angle right there. And so you would solve for time, and you get, well, if that's 1.3, this would be 2.6-ish. Now, the simpler way of doing it is, again, symmetry. I know at time is equal to 0, it's here. At 4 seconds, it's back at the exact same spot. Which means how long does it take to get halfway? Or in the case of the spring here, I pulled it down and I let go. If that's 0, how long does it take to get to the peak?
Twice a minute?
If it takes 4 seconds to do the entire trip, how long does it take to do half of it?
Oh, 2.
Yeah, it takes 2 seconds. So that would be 2 seconds. The first time it hit this, I was 0.7 seconds away from the endpoint there. The next time I hit it, I'm gonna be 0.7 seconds away. Which puts me at 2.7 seconds. And my crude approximations failed me here, but. But it takes the same amount of time to get to this location to its maximum value as it does to get from its maximum value back to that location. Questions, comments, concerns, confusions, contributions? And then how fast is it going? Once you have the times, just plug into whatever equation you have for velocity. That'll give you velocity, and then absolute value for speed. I can't remember if I asked for speed or velocity there.
Velocity.
Okay. So you plug into the velocity equation. Or you do a conservation of energy. Other questions at the moment? And using those 2 times when you're finding, if you found the speed would be the same. The velocities would be opposite signs, but the speed should be the same. Because your kinetic energy is the same at that spot. All right, so at this point we have 3 piles, right?
Yeah.
Okay. Actually 4 counting this.
Oh, you might put our master set in that box, I put that in one with the last.
It's all gets, I'm fine with 1 pile, I'll put it all together, I'll find it, if it's up there. All right, so some good news. We're done with chapter 21. I was looking back through, I was thinking there was still some other topic I was gonna hit, but there's not a need for that. So, yeah, this textbook breaks things up a little bit differently than my mind is set for. So it messes me up. Which means, time for assignment of master set and quizzes. Or quiz.
Is there a master set for chapter 21?
There is now, yeah. That's one of the things I disappeared in my office for, just to see if we were there. Yeah. It's there now. So I'm thinking the quiz on 21 on Thursday.
Okay.
And then, see, that's the 12th.
Like, I mean, that's upcoming?
Yeah, in 2 days.
In 2 days, oh god.
What are you talking about? This week?
Yeah.
Yeah.
Oh,
The-
God.
the quiz?
Oh, boy.
For chapter, whatever I just said, 21.
And we have the other lab due that Thursday too, don't we?
Yes.
Which one's that? That's the standing waves.
Right.
I was gonna put the master set due on, yeah, but that goes really well with chapter 21 though.
I'd imagine so.
Yeah, life doesn't always work that way, but it happened to in this case. I'm just trying to think of how much of a burden this is for Thursday. Is that unreasonable?
Is the next lab gonna be on Thursday too? Or is it gonna be tomorrow?
I suspect it'll be on Thursday also.
So we have a quiz and the lab on Thursday.
Oh, yeah, that does cause an issue there.
What are we talking about, the master set being due?
Alright, are you good with the quiz and the master set on the same day? Master set due the same day as you do the chapter 21 quiz?
I don't mind.
That works. I mean, no different than the day.
Yeah, it's only because I forgot on Thursday. Alright, so master set, we'll make the master set due a week from today, the quiz on chapter 21, the homework quiz on chapter 21, a week from today. And then, alright, so cross that one out, and then lab, this was the vibrating string lab.
Mhm.
Big string due, alright. Alright, and for all those fans out there in the world, we've got or at least the ones who missed class today and are watching us. So the quiz, homework quiz on chapter 21 is a week from today, so that would be the 12th, I believe.
Yes.
And the master set for chapter 21, which is now posted, also due a week from today. Any questions at the moment? Let's take a look at chapter 22. All right, what frequencies are those?
Sound wave?
What was that?
Sound wave?
Oh, they are sound waves, definitely. Frequency? Can anyone figure it out?
Well, it's in between our human range of hearing, so.
All right.
Like 6.
I don't know.
And the units for that are just 6. 6 in the correct units.
It hurts, sure.
Oh,
Let me play you what, oh, actually, it's thing on. Let me play you what 6 hertz sounds like.
You
Alright.
can't hear 6 hertz.
Oh, maybe he can.
We're gonna have all dogs howling outside.
Let's turn that on. There we go. There's 6 hertz.
Oh, yeah, I can hear it.
Yeah.
Yeah.
Let me play 200 hertz. Or 5200 hertz. There we go, 200 hertz. That's 200 hertz.
Yeah.
That sounds like a higher frequency than 200 there. All right, let's see if we can actually predict it.
Okay.
Now, when we were dealing with the vibrating string or in the hallway, we had nodes at the ends. We had 2 fixed ends. But a tube like this, it's open at both ends, so those are 2 free ends. And if there's a free end, are we going to have a node or an antinode?
antinodes.
So the simplest pattern I can come up with, so what, the first harmonic. Wow. I had some of the right letters in there. All right, so the first harmonic, we have a note at each end, and so the simplest pattern looks like this. So if I could, the trouble is, if I put a device in here in order to actually find out that it's silent in the middle, it would disrupt it, and you wouldn't actually get the pattern. But what you're gonna hear for the first harmonic is basically you have two free ends here, or two antinodes here, and I got a node in the middle. The next harmonic that I can produce, well, I still have to have two free ends. And I'm gonna redraw this just to give myself more room for the next stuff. So I've got a node here, so I'm gonna start up high, down, and then up again. That would be the second harmonic right there. Not necessarily legible, but spelled correctly at least. How many, the first harmonics, how many waves?
Half a wave?
Is it half?
Yeah,
Why?
it doesn't like complete, like neither end completes a wave.
So you're going with, basically we just chop those two ends off?
Yeah.
Yeah, that's a half a wave. So whatever this length is here, that length is a half of a wave. So the wavelength that of the sound would be, well, just solve for lambda, it's just 2 times whatever the length is. We'll get to the frequency in a moment. Second harmonic would be how many waves?
One.
Just like before, every time we get to the next harmonic or next overtone, we are adding a half a wave. So the wavelength would just be whatever L is. The next harmonic,
Be 1.5 waves?
and so lambda is equal to, that's 3/2, so this would be 2/3 of the length. That's the third harmonic. Now let's figure out what the frequency is that we actually hear for these. So that's why I brought this out. We're gonna do a little side trip down speed of sound. So, what the frequency we hear depends upon the speed that the sound is actually going to travel. I know that the speed of the wave is frequency times the wavelength. And I have some, if I measured the length here, I would have the length, but I need to know the speed in order to figure out the frequency. So the speed of sound in air,
343 meters per second,
ish,
340.29.
still ish, there's a formula. It is temperature dependent. Because sound is traveled in by the molecules in air, and the hotter it is, the faster they're moving. So you're not necessarily getting better clarity of sound with hotter weather, but the sound is going to travel faster in hotter weather. So 331.3 meters per second times the square root of 1 plus the temperature in degrees Celsius. This is a theta, so this is temperature in degrees Celsius over 273.15.
Isn't that 273.15?
Yep. What is that?
Absolute zero?
it's related to it.
Is the, if it was negative, it'd be absolute zero.
Yeah.
Yeah.
But it,
I don't know how to say that. Scientifically,
it comes from the absolute scale to this. Matter of fact, if we go ahead and, I got 1 plus this, let's go ahead and add the fraction together. So 331.3 meters per second times the square root of, common denominator would be this, so this is 273.15 degrees Celsius plus your temperature in degrees Celsius divided by 273.15. It's always a funky thing going on with units when you do the Kelvin degrees Celsius relationship. But if I take a temperature in degrees Celsius and add 273.15, I have the temperature on an absolute scale.
yeah, Kelvin.
Yeah. So this becomes 331.3 meters per second times the square root of the temperature. And yes, it is the same symbol we used for the other one. This is the absolute temperature. In Kelvin. Divided by 273.15. I guess that's how it goes, So right now, our temperature is 22.1 degrees Celsius in this room. We add 273.15 to it. So 295.25. Now this class is officially, this gets into some thermodynamics that's not really part of the class. If you've forgotten, 0 Kelvin is called absolute zero. It is the temperature at which,
No molecules.
what'd you say?
No molecules move.